welcome to the module. In the last module, we have seen the relationship between V in and the change in the frequency of the encoder. So, we have also understood the working of driver circuit, how exactly the driver circuit is working, and we have also seen the relationship between input voltage, that means input connecting to the positive terminal of operational amplifier, how the frequency of the digital pulses that we are getting from the encoder is keep on varying. So, as we know that encoder depends upon the number of pulses that it is coming, entirely depends upon the RPM of a motor. So, increasing the voltage increases the RPM of the motor. So, as a result the number of pulses that we are getting per minute is also increasing. So, as a result we have also observed that the number of pulses that we are that it is occurring or we are getting from the output of an encoder is also higher. So, one way to visualize that is by looking into the frequency, and we have also seen the frequency, and we have divided the frequency that we obtained from the CRO using RPM divided with 14. The purpose of this 14 is that when we looked into the data sheet, one revolution corresponds to total of 14 number of 14 pulses. So, we got an RPM. So, finally, we made a graph between V in and the RPM, and we understood that by plotting a trend line, we understood that 1 volt is corresponds to approximately of 20 RPM. So, what it means, if I want motor to be rotated approximately of 20 RPM, if I provide a set point of 1 volt, it will understand that the motor has to be rotated at 20 RPM. So, that is a scaling factor or a mapping factor that we have concluded from the yesterday's experiment. So, with this understanding, we have also done the simulation of converting the input digital pulses into the constant width pulses by using a monostable multivibrator. So, why do we require this? When we observed the Excel, which gives you the plotting, which gives the relationship between V in and the frequency, along with the frequency we have also observed the on time and off time of the pulse that we are getting from encoder. So, when we observed both the frequency term, the pulse width, everything is keep on varying with respect to the input voltage. So, if I directly integrate the input voltage, it is very difficult to get a relationship between the output voltage and the input voltage, which is nothing but the RPM. So, for that purpose what we have done, we have made one particular term as a fixed. So, either we can make RPM as a the frequency at which this particular thing is operating to be fixed, and by varying the by changing the pulse width, which is nothing but a PWM signal, we can also integrate that signal. We can understand, we can observe the varying output voltage with respect to the change in the pulse width. But since it will be a difficult, what we have done is we have interfaced, or the output of the encoder has been integrated to a monostable multivibrator. So, since it is a monostable multivibrator, whenever a triggering pulse is received, whenever we receive a triggering pulse, at this point we will get a constant duration pulse, and this constant duration pulse, either this or this one. So, in this case, so since it is a monostable, that to operational amplifier based, we got a pulse like this, and this duration of the pulse entirely depends upon the parameters that we have set here, not D. So, it depends upon the beta, it depends upon R1 and C1. So, those relations also we discussed yesterday, right. Then we have also seen how we have come out with the R1 C1 values as well as R3 R4 values in order to match with all the operating ranges of our input voltage, which means that when the motor is rotating with 0 to 5 volts, whatever the frequency the output encoder is providing, the monostable multivibrator should work for all that operating range, all the frequency. For that we have chosen such that the charging and discharging time of the capacitor should be always smaller than that of the monostable multivibrator pulse value, as well as should be smaller, the charging and discharging of the capacitor of a monostable multivibrator should be smaller than that of the lowest value of the encoder signal that we received. Since the operating voltage is of 5 volts max that we are using in this particular case study. So, for 5 volts we observed what is an on time as well as what is an off time, and if we know on time and off time of the pulse, by adding both the things we will get the total time, and this total time is smaller is higher, this total time is higher than the total time that we got from discharging and charging of a capacitor. As a result, this will work completely for that particular range of input voltage or particular for this particular frequency signal. And also the discharging time of the capacitor which is decided by R1 and C1 should be smaller than that of the discharging time of the pulse, right. So, with this understanding we have considered the R1 as 3.3 kilo ohms, C1 as 0.22 microfarad, and beta instead of going with 0.5 for our requirement we have gone with 0.3. So, with this understanding, now after conducting an experiment yesterday, we understood that for all range of input voltages from to the motor, which is 0 to 5 volts, the encoder changed its frequency from approximately of 227 Hz to 1 to 5 volts, 227 Hz to somewhere around 1.5 kilohertz. So, for all this frequency we understood that the monostable multivibrator is working fine and it is as per our expectation. But now what we have to see, our intention when we recall into when we look into our complete closed loop control system block diagram, the whole idea is that the system input should always map with the output that we get from the sensor. But right now we have done a part of sensor signal conditioning. Since we already have a sensor, a part of sensor signal conditioning, that part is designing a monostable multivibrator. So, so that after monostable multivibrator we got a fixed time duration of a pulse, either it is on time pulse or off time pulse, one particular pulse is always fixed. And we have also seen that in order to make that, the output of the encoder in this case, which provides a triggering input to the monostable multivibrator, should be always from 0 to minus 5 volts, right. So, the next part is that next part of signal conditioning is that this pulse has to be converted to output voltage, right. And after generating an output, that too linear output voltage, what I mean is that by varying the RPM of an DC motor, which varies with respect to the change in the input voltage given to the DC motor, the output voltage also has to linearly increase. So, which means if I say this is an RPM and if I say this is sensor signal conditioning circuit, so based upon the RPM, the sensor signal conditioning circuit output should also vary linearly, but at what rate? This rate at which it has to operate should be equal to the mapping factor of your system input. So, in this case our mapping factor is 1 volt corresponds to 20 RPM approximately. So, which means that 20 by 1, so 20 RPM per 1 volt. This is a sensitivity factor or the mapping factor that we have considered for this particular system. So, whatever the output that we get from the sensor signal conditioning circuit should also maintain 20 volt per RPM, 20 RPM per volt. Or 1 volt per 20 RPM. So, in this case input is RPM, output is voltage. So, that is why it is 1 volt per 20 RPM when we consider as a sensitivity. So, as long as this condition is satisfied, our signal conditioning part is done. but we have not still reached to this particular case. Before this case we have to get an output voltage, but how do we get a linearly varying output voltage? So, in order to do that, today what we are going to see is that we are going to integrate the output whatever we get from the monostable multivibrator, but instead of directly connecting it to integrator circuit, we are connected through an inverting amplifier. But why do we require an inverting amplifier? The reason is that yesterday in the previous session, if you observe, the output that we get from the monostable multivibrator, meaning when a triggering pulse is given like this, so this is from encoder output, right. So, this is 0 volt, this is minus 5 volt, because we have reversed the clock pulse. And it has been given to triggering input of a monostable. Multivibrator. So, we got an output such that the output will be always from plus 15 to minus 15. So, we got something. So, if I say this is plus 15 range, and if I say this is minus 15 range, minus 15 volts range, sorry, this is minus 15 and this is plus 15 range, we understood that whenever there is a negative spike, we got, so in this case there will be a negative spike at this point. So, we got a fixed pulse with a duration of 279, approximately 280 microseconds. So, we got something, we got like this, this is 280 microsecond, and till we get a next triggering pulse, it was in stable state, that means at plus 15, right. So, this is the signal that we got, and this signal width is also smaller than that of the complete signal, but ideally practically there will be always a difference. The reason is that when we see ideally, we always consider that op amp output voltage will be supply voltage plus 15 and minus 15, but practically speaking the supply voltages will not be at plus 15 and minus 15, will be smaller than the supplied voltage. As a result, there will be small deviation in on time as well as on off time of the output of monostable multivibrator. But after considering everything, we have given a very big room in this case, where we require a total of 620 microsecond, but the complete ideally it is 516 microseconds is the time required for the capacitor to charge as well as discharge in this case. So, we have plenty of enough time in this case for sustain for those practical problems. But even then, but if you see during the negative cycle, the output is very smaller. So, what we have done is, by passing through inverting amplifier, the output will be a phase shift of 180 degree phase shift of this particular signal that we have seen. So, finally, we get a signal of like this. So, whenever there is a negative triggering pulse, this particular width will be 280 microsecond, and this will be based upon the previous state, next triggering cycle that we get, right. So, this we have already this will be the output of an inverting amplifier. For further details about inverting amplifier, I suggest you to look into the previous course, which was discussed by Professor Hardik Pandya. Now, so this is a practical integrator. The difference between a practical integrator and ideal integrator is that the practical integrator should always have to have a resistance R5 parallel to the capacitor that we have seen here. So, even this integrator concept we have discussed in the previous lecture, please previous course, please have a look if you have any further information, or you can even send us an query, so that we can give you further more information about that. Now, we will see by varying this particular frequency, the encoder signal frequency which has given as an input to the monostable multivibrator, whether we are getting a linearly variable output voltage or not. The whole idea is that it has to give a linearly variable output voltage based upon the change in the frequency. So, we will see how whether it is giving it or not, but what is an idea behind that, that adding an integrator to the output of a monostable will gives an linearly output voltage. The reason is that, so when we look into the monostable multivibrator, we know that we are getting a fixed duration pulses of on time pulses, but generally it will be reversed. Since we pass it through a inverting output, this fixed duration will be on the positive side. Say this is for one particular set of frequency, right. Now, for example, say in this case we have seen only 3 pulses, 3 on time pulses of fixed duration. Suppose if the input voltage given to the motor has been increased, what happens? For the same fixed time duration, say this is time t1, for the same t1 we can see more number of pulses. Right, we can see more number of fixed number of pulses. So, because this constant is always fixed, and this entirely depends upon monostable multivibrator that we have designed. Even in this case, this is Tx, this is Tx, this value, and this is also Tx, but the number of such Tx, these pulses occurring in higher frequency signal is higher than the low frequency signal, right, which means that for when the input voltage to the motor is higher, we get more number of such pulses. When you integrate this particular curve, integrate this particular output voltage, in this case the area under the curve will be smaller, in this case the area under curve is higher, but it entirely depends upon what is your plus VCC as well as what is your minus VCC too. Since in our case plus VCC is plus 15 and minus VCC is minus 15, right. Initially it may be at one particular value, it will be keep on decreasing, because the magnitude of minus 15 is higher when compared to the magnitude of plus 15. So, when the RPM is higher, the magnitude of plus 15 is also increasing when compared to minus 15. So, we may experience a negative slope curve, right. So, we will see how exactly it is going to come. So, let me open Multisim here. So, yesterday we have seen the working of this particular block, which is nothing but our monostable multivibrator. We have given an input signal which is similar to the encoder output that we receive, and this is our integrator circuit which we have seen at this point. Similarly, this is our inverting amplifier. So, now what we are going to do is that I have already designed an integrator and kept it here. So, this yesterday we have already seen in the previous module. Just have a look on the previous module in case if you have not looked into that. So, now we will vary frequency at this point. So, we have already noted different frequencies, the frequencies that we got from the yesterday's experiment, from the previous experiment. These are the frequencies that we receive. We provide an input of these frequencies at this point, and we have also observed the output voltage is there yesterday in the previous course, in the previous module. Now, we will see whether the output is linearly varying or not. We will do the simulation, then we will note down the values, then we will also experimentally verify whether we are getting a linearly variable output voltage or not. Now, what I will do is that the first frequency, so these are the frequencies we got. First I will apply 227 hertz signal here. So, this I will change it to 227 hertz, and I am running the simulation. I will go to Grapher. So, our interest is only to the integrator output. So, this is our integrator output, we got somewhere around 10.21, 10.215. Let me note it down. So, we got 10.215, because why I have given at input voltage of 1, because for input voltage of 1 we know 227 hertz. So, that means when the motor is connected with 1 volt, the output we are getting from the integrator is 10.215 volts. Next, we will apply the another frequency. So, the other frequency is 357, right. Here we can see the in output voltage is decreased. I hope now this is clear for you why the output voltage is decreasing. So, it is 9.11, 9.11 volt. Then I will go with 2 volts. So, 2 volts corresponds to 515 hertz. Let me stop and run. So, we will wait for 1 second. So, right now it is in milliseconds range. So, when I look into the value, we got somewhere around 7.9. So, we got 7.9 volt. I will go with 3 volts now. Let me stop. So, 3 volts corresponds to 827 hertz. Let me run. So, I will wait till 2 seconds here. So, that it is just like, since we are using a capacitor, it takes some time to charge it too. So, we got approximately a 5.2 volts. So, let me write down 5.26 volts. So, not here. Then we will go with 4 volts. So, the 4 volts corresponds to 1.157 kilohertz, 1.157 K. We will wait for 2 seconds, 1 to 2 seconds, because right now it is running at milliseconds range. So, now it is 2.7. So, I will write down 2.7 for 4 volts. Then we will go with 5 volts. Let me stop. So, 5 volts corresponds to 1.483 K, that is what we have observed yesterday. And let me run. Now, if I notice it, we got somewhere around 200 millivolt, but it is keep on fluctuating. That is because of the capacitance value. If you slightly increase the capacitance, then the problem would be solved. So, 200 millivolt, sorry, yes. So, let me change the capacitance to little higher value and observe. So, so here we can see approximately of 200 millivolts. Now, with this understanding, so these are the values that we got. Let us plot these values in an Excel. I will take one more sheet, or I will take in the same sheet. Let me keep it aside. So, this is for integrator output, I am calling it as VO1. So, we got 10.215, then for 2 volts we got 7.9, then for 3 volts we got 5.26, then 4 volts 2.7 volt, volt, then for this 0.2 volt. Now, let me plot the graph between input voltage and the VO1. So, here we can see we have R square value of 99.9 say 0.99, which means almost linear, but when we see the slope that we got is negative, which means that when the input voltage is keep on increasing, the output voltage from the integrator is keep on decreasing. That is what even we have expected from the previous graph. That indicates the slope is of negative. The reason why it is we are getting a negative slope is that when we look at when we have done an analysis, we have already shown that we have already seen that the output from the monostable multivibrator as well as in integrator pulses will always will fluctuate from plus 15 to minus 15, right, and the magnitude of minus 15, the time duration of minus 15 is higher when compared to the magnitude of a plus 15 volts. So, as a result, when we do an integration, which is nothing but area under the curve, the magnitude initially will be higher when the RPM is keep on decreasing, as the magnitude, the time duration of the 15 volts is becoming higher and higher because of more number of pulses that we are getting it. So, that the magnitude of the positive is higher when compared to the magnitude of negative, resulting to decrease the output from the integrator. So, that we can even see at this plot itself. But what we require? We require the mapping factor of 20 RPM per 1 volt. Every 1 volt we have to get a volt output of 1 volt, but from this case we got somewhere around minus 2.53 x into x plus 12.84. Let me write it down, minus 2.53 x plus 12.84. The slope of this line is minus 2.53, but we require a slope of 20 positive 20, but how do we convert it? How do we convert it is a question mark. So, that means we have not completely fulfilled the requirement of output voltage of a signal conditioning circuit. Still we have to design another set of signal conditioning circuit in order to map the input set point to the output voltage of an integrator.